let's continue the second part. So after solving the wave equation, we found out that we are doing the approximation, which pretty resemble or looks like the finite quantum wheel result. And let's just do the side-by-side comparison like our newspaper like to do. Alright. So this is the case of finite quantum wheel we did in the lecture 2. And this is the slab waveguide we just finished. So the governing, what's the governing equation? The governing equation of the quantum wheel is called the Schrödinger equation. But from the point of mathematics, it's a Laplacian equation with eigenvalue problem. Alright. Similarly, for the slab waveguide, it's also a Laplacian equation with an eigenvalue problem if you take the NEFF to the other side. It's pretty the same. Alright. Only the difference is that we have a negative value here, so we have a positive value here. And what I was trying to solve. For the quantum wheel we are trying to solve is eigenenergy. The energy is the thing we need to we want to know. In order we want to know what's the energy difference between the ground state in the conduction band and the valence band. In the slab waveguide, since Nx is the given reference index profile, this is not what we want to solve. This is what we have at the beginning. So what we want to solve is actually u of x. But while solving u of x, we need to know the NEFF first. So actually we are finding the effect index, which will satisfy all the boundary conditions for the boundary equation. And then the final solution, if we have eigenenergy, then the bound state, the energy state, or the wave function will be directly obtained with some little effort. Similarly, if we have NEFX, then we can construct the optical mode. Since we have NEX, we can solve the K and the gamma in the previous case. Okay, so the optical mode. And the fundamental solution is, for the finite quantum wheel, the fundamental solution is called the wave function, it's lowest energy. And the slab waveguide is because we have a minus sign here, so the term is opposite. So the slab waveguide gives you the optical mode profile with the highest NEF. Or for the slab waveguide, it is the resonance with the largest angle. So we can look these two pretty alike from the point of either in physics or in maths. So we can see each other with a cross interpretation that a quantum wave is actually a slab waveguide for the particle wave. And the optical mode can be seen as an energy state for the quantized body. Only for if we have an optical mode in the semiconductor cavity, that means a photon with certain frequency can reside in such cavity for a long time. So it might have the longer interaction with the materials. So the light matter interaction will be prominent or be very important. Yeah. So it doesn't sound like the electron and the photon now are the same thing. But not really. So we call the wave particle duality. It's not only for electron, but also for photon as well. Alright. So we need to really solve the numbers in order to calculate something called the confinement method. So the question is how to obtain such an EFF. This is the more general case that if the N1 is not equal to N3, then you have gamma 1 and gamma 3, and the K is incumbent. Then you need to solve the boundary equation at both sides. So this is one of the extra homework. If you can derive this term, you get the directly one point bonus from in the final. Because this is only 10 years, this is not difficult. Yeah, only 1 point. Okay. So, but I will skip that because we are not really doing the mathematical research in major case. This is only for you. Look, now we have the V as an indicator of how strong the waveguide is. What does it mean a strong waveguide? That means you either have a very strong index difference between the layers, or the thickness is big enough. Yeah, that means you have a stronger waveguide. If you have a strong waveguide, you have more solutions available up for more. So this figure is pretty like the one in the common world. It comes from it just gives you different V and records the different effect index and then plot it one by one. Then you got so it's important to know how to read this figure. So the y-axis is the B. What is B? B is also a uniless value which involving the NEFF. For general asymmetric case, we lack the reflecting probabilities. Okay, so it's asymmetric. So it is reasonable to assume one of them is higher. So we call it N3. And the lowest is called N1. And the highest in the middle is called N2. So the B positive. Okay, so this is also let me double check. Yeah, this should be N3. This should be N4. This should be N3. I think this is a typo, but since all of the question don't encounter that problem, so I'll double check and download a final version probably today. Alright. So let's consider a case of N3 over N2 over N1. So the first is I think this should be N3 because it is meaningful to evaluate the one with a larger index. If this is small, then will become more. So V is the first is the difference between the N3 and N1. So V is square root and N2 square minus N3 square KD. Okay. Second is the asymmetrical how asymmetric of such a guy is. So the denominator is that N3 squared minus N1 squared. Normalized to N2 squared minus N3 squared. So if it is symmetric, if N3 equal to N1, then A is 0. Alright. Second, if N2 is very close to N3, but N2 and N1 is finite. For example, the waveguide looks like this. Okay, so this is also a very bad waveguide. You have only a small difference at one side, but finite width at the other side. So in this case, N3 minus N1 is a finite value. This is N3. And the N2 and the N3 is very close. So this waveguide is very asymmetric. So A goes to infinity. The worst case. That means one side of that has almost no reflected index. Okay. So after solving this equation and plot it one by one, the final figure looks like this. Alright. So, for example, for a symmetric waveguide, you might have B to be 2. Then, with the B equal to B2, you will find the B should be around 0.45. You have a number of B. You can solve its NEFF. Alright, so this is the digestion of the graphical approach. 就是他把刚刚那个图经过消化了，用每一点画出来像这样子。You see there's a small figure called A is equal to 0. That means it is a symmetric case. If the optical mode is very asymmetric, means A is equal to infinity. So this is the first term, A is equal to 1, A is equal to 0, A is equal to 1, A is equal to 10, A is equal to infinity. So if your waveguide is very asymmetric, you might have no fundamental mode. That recalls the homework number 1. If you have a symmetric quantum well, it is possible that you don't have any ground state of that quantum well. Anyway, so first, stronger the waveguide. For example, if you have a 10 here, you will find at least 1, 2, 3 available mode. But if the waveguide is weaker, you intentionally make a waveguide weaker, you might have only one fundamental mode for such a waveguide. Alright. So the calculation procedure is like this. First, with a given reflected index profile and the structure, you can calculate V. And the A as well, but for the symmetric height, the A is equal. So after you have B, you can calculate B. After calculate B, then surely you directly find the NEFF. So the difficulty, the major difficulty is how to find the B with B, because the rest of them is simple algebraic calculation. You just put it in the calculator and already get it. So this is a good approximation to build the relation between B and B. It's also the memory of this textbook. It really cares about whether you can get a number with a simple calculator. So you have no excuse that, oh, I understand that, but I just don't know how to get a number because the figure is not accurate. Sorry, this textbook is made in order to, you should do really some homework with your bare calculators. Alright, so after you calculate B, we suggested that the B for the fundamental mode, okay, because only fundamental mode is important for the most of cases. B can be approximated as 1 minus 2 times natural log 1 plus squared divided by 2, then divided by B squared again. Alright, so how accurate is that? This is such accurate. I intended to make it bigger, much larger. So instead you need to calculate that and find the value, you have a better figure. So the back curve is the resolution. And the first curve is the fundamental mode. The first point you will encounter in the tangent and the plot we showed 1 hour before. So m is equal to 0, it means the fundamental mode. So this is the second order mode, first order mode and the second order mode. And this is the plot directly by itself. This is B is equal to 1 minus 2 log times log of 1 plus B squared divided by 2, then divided by B squared again. Okay, so this is the blue curve is the exact term, and the blue curve is the approximated curve, and the black curve is the exact one. So actually, that's pretty good. At least by eye or by feeling, it is a good enough approximation for you to do the real calculations. Alright. So now we need to define the important term for the confinement factor. Confinement factor, by words, it tells you how good the photon should be confined with such waveguide. So for waveguide, if the field is outside the waveguide, it will eventually leave this cavity. So it is not useful. Only the field intensity within the waveguide could be regarded as a photon trapped in the particle mode. And the photon, number of photon is the energy of photon. So it should be proportional to the square of the field. So the confinement factor could be doing just like this. You do a square of the electric field, then integrate over the intensity region. For such waveguide, the intensity region is from -2D to half of D. So gamma X is the field integrating in the guiding layer divided by the integrating all over the space. So it should be a number less than 1 for most of cases. But in some extreme cases, because you will adopt another definition of optical confinement, it's possibly to be larger than 1, but that will be not the case here. We were taking the more general and the simple cases. Okay. And since the waveguide here, it could be written as a cosine and the exponential. So the integration is actually not that difficult. A little bit tedious, but not that difficult. So after doing some basic fundamental of integration, you will see the gamma X could be evaluated with as this 1 plus 2 gamma D divided by V squared divided by 1 plus 2 divided by gamma D. Alright. What does gamma? Gamma is here. If you have B, you have NEFF, and you have NEFF, you can calculate gamma here. NEFF minus N1 times square root times 3. So you also can calculate gamma if you have NEFF. Gamma D is equal to take a square root NEFF squared minus N1 squared K0 D. And we can do that as NEFF squared minus N1 squared divided by N2 squared minus N1 squared and times N2 squared minus N1 squared K0. Alright. And the first term is square root B. The second term is B. Then we put it back to the first equation. So this is the exact solution. This is not an approximation. This is also one of the other additional homework. This is just a practice of your calculus. But you need to also need a strong sense to simplify it down to that. So gamma X is equal to 1 over 2 gamma D over 1. and 1 plus 2 gamma d divided by b squared, and it is 1 plus square root b squared equal to 1 plus 2 square root b over 1. So it is 1 plus, and when we can times b at the both side and the both ends. Okay, so it becomes b times 1 is b plus b divided by b, nothing. So plus 2 square root b, and in the denominator similarly, plus 2 times square root b over 1. So it turns out that it is b plus 2b squared and b plus 2b couple squared. Inverse square root. Okay. So that's the most elegant form we can get. As long as you have b, you get a b, you get a b. You get a b, you get a gamma. So the calculation is actually pretty straightforward. If the b is pretty small, if the optical mode is pretty weak, yeah, you can do the Taylor extension of such law. Then you will get a even simpler approach that the gamma x is equal to b squared divided by 2 plus b squared over 2. So this is only an approximation. In practice, you only need this equation because they will be, firstly, it is not too difficult. Yeah. Second, it fits for OB of the grounded state. So I think this one is already good enough.